Welcome back to ECE 320. Homework number 1 is due on Sunday. So if you have a test on Monday, you may want to start working your homework now. Homework 2 is due the next Sunday, and exam 1 is the following Thursday. And there is exam 1 material posted on D2L if you want to see some of the structure or types of exams. I will warn you that some of the summer practice exams do not include all of the material that you will be held accountable for on your exam. I don't think they get into three-phase power. Today what I want to do is get into three-phase power, but before we do that, I want to work through an example of power factor correction and make sure that that's clear. And that actually has some application for one of the homework problems, at least one of the homework problems where you're trying to investigate what value is this X sub L in my transmission line. What is that doing? And I hope that with the visuals in this example of power factor correction, it will give you a visual way to understand what's going on in terms of what you may need to do for the numbers or the equations. You should be starting to work or study through chapter 11, which is three-phase power. We will look at a high-level block diagram. We'll discuss some of the reasons why or the characteristic behaviors of three-phase power, and we will start talking about balanced three-phase systems. That just means that everything looks the same in all the phases. You are just out of phase with the A phase, the B phase, and the C phase. As you've learned already, we get very creative with our labeling in electrical and computer engineering. We have three phases in three-phase power, and we call them A phase, B phase, and C phase. A, B, C. And whether we say ABC or we say ACB, that indicates what kind of a phase sequence it is, whether it's a positive phase sequence or a negative phase sequence. And that's what I'm trying to say in this notation. ABC is positive, ACB is negative. And we'll draw a picture of that, and hopefully it will become very clear what we mean by an ABC phase sequence. But essentially, you are splitting a pie, if you wanted to think of it that way, into three equal parts. And they're 120 degrees apart. If you had to cut a pie in three, and it's not 3.1415, it's not that pie, it's like a cherry pie or an apple pie. If you now have a pie, and now I'm really hungry, how do you cut it equally into three pieces? Well, you would be cutting at an angle of 120 degrees. And that's really what's separating each of these phases, A, B, and C, in this three-phase power system. Then we will talk about the different ways that we can interconnect these systems. We could have sources that are interconnected two ways. They could be connected as a Y, and that I will probably just label as the letter Y, but it's very consistent with the pattern that it's configured in, or it could be configured in a delta. And your loads could be configured as Ys or deltas, and obviously then you have all sorts of combinations, not that many, 4 different combination possibilities in terms of how do you connect sources and loads if they experience or if they're interconnected themselves in one of these two ways. And these phrases, I hope you will just be dreaming about them for the next few weeks, okay, as far as ABC, ACB, Y connected, delta connected, etc. That should just start becoming second nature to you. But the nice thing about playing with balanced three-phase systems is we can actually convert those into a single-phase equivalent circuit, and then you just have to analyze that single-phase equivalent circuit, and that's like a KVL problem. And that's what we've been doing all semester so far, is a single phase sinusoidal steady state problem. And that's what we will boil it all down to, but you have to be comfortable making those steps to obtain or get to that single phase equivalent circuit. That's what we are hoping to achieve. I was just in a meeting and Siri started coming out of the seat. So somebody set off their phone and they were asking Siri a question somehow, and they didn't know it. I said, "Hey Siri." He didn't think it was very funny. Power factor correction. What are we doing? We have some original load, and that might be 3 or 4 different loads or 10 different loads all combined into what I'm labeling in this cloud as your original load. We're assuming that that is inductive, and now we are trying to essentially reduce or eliminate that positive Q by introducing this capacitor, this Z sub C. That's the idea behind power factor correction. What influences our power factor? If I say power factor, what are you seeing? You're seeing an angle, aren't you? Well, I like this. You guys are starting to play along, and hopefully nobody's listening. You're seeing hypotenuse, angle, horizontal, vertical. Siri may be even starting to do that in a little bit. But now if I say power factor, you're seeing an angle. If I say you have a power factor of 1, what is that angle? 0. You have all real power. If I say you have a power factor of 0.7 lagging, what are you seeing? What's the inverse cosine of 0.7, or what angle when you take the cosine gives you 0.7 roughly? 45. So now you're seeing a 45-degree angle that's positive if it's inductive. By power factor correction, what we are trying to do is get that angle that might be large, 45 degrees, smaller. We're trying to get it closer to 0. The ideal is to introduce this capacitor in such a way that the source, seeing that combination of capacitor and all of that load, to the source it looks like a pure resistive load. And the power factor of that combination is 1. That's what we're hoping to achieve by introducing this capacitor Z sub C. Everybody getting this mental picture of what we're doing? That's what we want to do in the first part of today's class. Here is our example from last time. I may slide through this very quickly because I'm assuming you already have this in your notes. But now we had identified 2 different loads, load 1 and load 2, with particular characteristics. Load 1 had a real power of 48 kilowatts, a power factor of 0.7, and it was lagging. Load 2 was 24 for its real power, or 24 kilowatts. It had a power factor of 0.96, and it was leading. Load 2 looks more capacitive. Load 1 looks inductive. The Q on load 1 should be positive. The Q from load 2 should be negative. Those should all just be triggered by reading that information. Last time I gave you a quiz. And that was to find this triangle. What is that triangle given load 1 information? And we found it. And last time we did it by using the Pythagorean theorem. But we started by using the fact that our real power is just the hypotenuse, or the apparent power, times the cosine of that angle. And the cosine of that angle is our power factor. To obtain the hypotenuse, we can simply divide the real power by that power factor to obtain then 480,000 divided by 6, or that now gives us 80 kVA for S1. That's the hypotenuse length. We know a squared plus b squared equals c squared. Now, in this class, it's p squared plus q squared equals s squared, the magnitude of s squared. Doing that, we found out, since we knew that q was positive, it was lagging, Q1 for load 1 was 64 kilivars. That we found last time. Again, I'm just going to scroll through this quickly because this is all review. That was 48 plus J64. Load 2, we worked. Let me work it two different ways. A way is just like we just did for load 1. Divide the power factor into the real power to obtain a hypotenuse of 25. This was now a leading load, or a capacitive load. Our Q is now negative. We'll assign a negative value to Q sub 2, and it ended up being minus 7 kilivars. This particular load is supplying magnetizing bars, the way the book is referring to it, and the other one is absorbing. Load 1 is absorbing magnetizing bars. We could have solved that by finding our angle first. In the first approach to solving for that second load's power triangle, we didn't even explicitly find that angle. In the second approach, let's find that angle first. And we know it's negative because it's a leading, or it's associated with a capacitive load. We now do the inverse cosine of 0.96, and that gives us minus 16 degrees. We can then again find our hypotenuse value by dividing the real power by the power factor to obtain 25 kVA, and then Q sub 2, which I'm running. That's the problem with doing this before lecture, is I don't know how my projector is going to scale my writing, so I didn't quite keep it in the correct width, but that now gives us, again, consistent with what we found the other way, minus 7 kilivars for Q sub 2. We can now start to, oh, and there's the power triangle for load 2. Horizontally, we were 24. The reactive power was negative. It was minus 7. And now S sub 2 is 25. So P squared plus Q squared is equal to the magnitude of S squared, the apparent power squared. Before we left last time, all right, I'm going to do this a little different. Bless you. Here's now the total load power sketched. I'm just attaching these complex powers head to tail, or tail to head, tail to head. To obtain the first head of the complex power 1, I just go horizontally 48 and up 64. That gives me S1 at the appropriate angle. And then I add to that S sub 2 by going horizontally and vertically. And you can see then what that second load is doing to the overall angle that you started with, let's say with load 1. The angle from load 1 is larger than the angle for the combination of those two loads, which means which one has a power factor closer to 1? Load 1 or the combination of the two loads? The combination. Load 2 is helping you to reduce that angle. it's doing some power factor correction for you. It's moving vertically down without going too far to the right, and that now allows us to have a smaller angle, net angle. If you algebraically added those up, S1 and S2, with their appropriate components, real and imaginary, we end up with the load of load 1 and load 2 looking like 72 plus J57 kVA. And I think we got that far last time. We could find the magnitude of that, or what's the apparent power, by just taking the square root of the sum of the squares of the component powers, and that ends up being about 92 kVA for the combination of those two loads. And the angle is about 38 degrees, which you can find that angle by just doing your trig and saying, what's my vertical distance divided by my horizontal distance, and I'll inverse tangent that. That gives you an angle of 38 degrees for that combination. If you remember the original problem, we were told the magnitude of the source in RMS, its voltage. It might be nice to know what this current is coming out of the source. And we can find its magnitude by realizing that we can use that formula for complex power. S is just VI star. And if that's true, we can take the absolute value of both sides, and then the absolute value of a product is the product of absolute values, which now allows us to find the magnitude of that current that's being demanded by those two loads. We computed our apparent power of the combination of loads 1 and 2 to be 91.8, or about 92 K. The voltage that we were applying was 500. We divide that out and we end up with 184 amps. Whew, that's a lot. That's amps. Doesn't take much to kill us, does it? Amps. Much less than 1 amp will kill you. Less than 1/10 of an amp will kill you. So that's a lot. 184 amps. Let's just look at that. Is the total current from the source. If we look at the two different loads, what are the magnitudes of those currents? We can do the same thought process. We know the voltage, everything was in parallel, and we knew the apparent powers for load 1 and load 2. We can do the same division to identify or find or compute the magnitude of the first load's current, which ends up being 160 amps, and the magnitude of the second current, which is 50 amps. And I think you can see that 50 plus 160 is not equal to 184. Those are just magnitudes. And remember, if we're trying to do a KCL or a KVL, we need to make sure that we're using complex arithmetic. We do things vectorially. Now, that was an aside on the currents. Let's go back to our power factor correction that we were trying to do. We found what was highlighted in the light blue. That was load 1 and load 2. We found those complex powers from the given information. What we now are interested in is determining this capacitor C that will in fact allow us to hopefully make that angle smaller in the overall system. Yes? The reason why we want, and I hope this example will help illustrate it, so maybe I should just delay the answer, but the question was, why do we want a power factor close to 1? I think that's what you were asking. Let's now figure out why that's true. But essentially, if we can introduce a capacitor, which is going to, what's its complex power going to look like? We know it's impedance, right? And it's purely imaginary. It's impedance of that capacitor in an ideal case. It's only going to give us reactive power if that's an ideal capacitor. There's no loss in that capacitor. There's no power absorbed. This capacitor is going to give us something that's vertically down. And we're assuming usually that most of our industrial loads in the real world are inductive, have a positive Q. We are trying to now make that angle smaller. The reason is that's going to require us to be requesting much less current from the power company. So it's going to make our pocket, talking about Siri now, we'll have more in our pocket. We won't have to pay the power company as much. It's an economic reason as one. And if we can reduce the magnitude of current flowing on these transmission lines, we wouldn't have to have as large of a system. Yes? Regular households are pretty much going to have a power factor close to 1. You, on your bill, I don't think will see, at a residential power bill, you're not going to see a power factor indicated at all. You're just going to see kilowatt hours. That's how much energy you are demanding over the course of a month. They are assuming that you don't have a lot of heavy equipment or machinery that looks fairly inductive. Hopefully your power factor is very close to 1. So when the power company is supplying you or this residential area, it looks fairly resistive, not very reactive. That sketch we should be okay with. All I've really done is said, let's now find or try to introduce this capacitor to make the angle of our between the real line or the real power and our hypotenuse or the apparent power. So we're wanting our apparent power to be about the same as our real power if we make that angle small. If it's 0, then they're the same. Here's another sketch. Let's now, in this sketch, combine everything. Let's say this is now S12. That's now 72 plus J57. And that's kVA. We now want to introduce this capacitor in parallel, let's say. Well, maybe what I'll do is I'll make it different. Sorry. Let me call this now some impedance with a subscript of C, meaning that impedance is the result of a capacitor. And we still have V sub G in terms of its magnitude is 500 in RMS. What are we trying to do? Well, we have this triangle right now that's 72 real, 57 vertical or reactive. We now have a total power without that capacitor This was now approximately 92 kVA, where this was Q12 of 57, and this P12 is 72. And I could even say that now I have this angle, theta sub 1, 2. And the question that we're really asking ourselves is, how much Q sub C, that's going to result from that capacitor's impedance, how much reactive power from the capacitor do we want from C? That's the question that we are really asking. And somebody might say, you know what, we have an angle. What was that angle? Did I say it was 38? Is my memory okay? 38 degrees. Maybe somebody says, you know what, let's get it down to 20 degrees. Then you would be saying, oh, I want to end up, after I introduce that capacitor, I want to end up right there with my hypotenuse head, the head of my hypotenuse, which means that I now need to move the tip of Q12 from 57 down some fraction to make that overall angle 20 degrees. Is that clear? Or maybe somebody says, you know what, if we get it within 5 degrees, we won't have a surcharge from the power company. So let's now invest enough in this capacitor bank to bring that angle down to be 5 degrees. How much is that going to cost us in terms of a capacitor? What we are going to do actually is we're going to bring it all the way to 0. Just for illustration, but you wouldn't have to. Is that clear? Now, how do we bring it all the way to 0? What's Q sub C going to have to be to bring Q, the total Q, when we have the load 1, 2, and the capacitor in play, and we want the reactive part of all three to be 0? We need it to be a negative 57, don't we? We now want to introduce this Q sub C to be minus 57, and I think all of these were units of K, weren't they? Kilovars, etc. So we want Q sub C to be minus 57 so that when it is added to plus 57, we will actually end up right there at 0. Is it clear where 57, minus 57 is coming from? Now let's figure out how we get there. And is it also clear that if we had a Q sub C of minus 10, that would still be beneficial, wouldn't it? If we had a Q sub C of minus 30, that's even better than minus 10. Minus 57 is going to get us right there. Yes? Yes. So the question was, is it possible to have bigger than 57 in the negative direction? And yes, you could have a capacitor that's now able to deliver more magnetizing VARs than you need. But you wouldn't want to get it too negative, because then your angle goes even bigger in the negative direction, and now you're having a power factor that's 0.7 leading, and the power company's going, you guys are just playing with me here, because you'll still be requesting a large magnitude of current to deliver that. more than what you would need to supply just the real load. We're doing this, we're trying to find that Q sub C from our capacitor. And this is what Dr. Marcelin taught you. What's the impedance of a capacitor in sinusoidal steady state? Thank you. 1 over j omega c, right? You all just said it in unison. So this is now 1 over j omega c. That's the impedance of this capacitor. What's the complex power of that capacitor? Let's say in terms of the voltage and current of that capacitor. VI star. This, again, you should be just singing that. You'll wake up in the middle of the night, VI star. Who knows what Siri's going to be thinking, right? But you now have this is the voltage of the capacitor times the current of that capacitor. Those two quantities are both phasors, and what else am I implicitly assuming? They're RMS units. And a lot of times I don't even write that down, but I'm assuming that all of those phasors are already in RMS units. That you know, VI star, voltage of the capacitor, current of the capacitor. But we have known to us the voltage that's across all of those parallel combinations of the loads and the capacitor. So let's try to rewrite this complex power of our capacitor in terms of voltage and get rid of that current. But we're okay to incorporate that impedance because we know what that is. We keep that, but now how do I write the current? This is Ohm's law generalized to complex quantities or phasors. Current is now just V sub C over, boy, where did I learn Ohm's law? V sub C over Z sub C, and I need to conjugate that expression. So that now I have V sub C star over Z sub C star. But what is Z sub C star? You just have to negate the imaginary part or the imaginary component of that impedance. It's all imaginary, so we just have to introduce a negative sign somewhere. Let's just put it down there with the J. I just need to negate the sign of the imaginary component of that complex variable, and it's all imaginary. Let me just negate that whole thing. Now, if I use that in this expression and knowing, what do we know about V star? Or any complex number times its conjugate is equivalent to the magnitude of that complex number squared. We now can say that the capacitor's complex power is the magnitude of that voltage squared divided by 1 over minus j omega c. And that's an ugly C. It's not much better, but that will jump upstairs or in the numerator, and now we have that expression for the complex power of our capacitor. An ideal capacitor. We're not assuming any losses, any resistance in that capacitor. This is an ideal capacitor. And what did you say you wanted S, or the reactive power, to equal of that capacitor? Minus 57K, right? And that Q was a minus J57 that we wanted to introduce. And what's omega? We know V sub C. That's the voltage applied across those loads, and the capacitor was one of those loads. That was 500. We know that. We don't know C. You just told me what S cap should equal. And omega is 2 pi F, which is 2 pi 60 in the United States. The reason I keep saying that is, what is it in Europe? It's 50. So it depends on where you're at, what that F might be in a power system. Or that's why you can't just plug your whatever into an outlet in another country. You need to make sure you know what's coming out of the wall. It may not be shaking as fast as we are in the United States. Right? We're at 60. Where was I? Shaking. This is now radians per second. And you just told me that we want the capacitor's complex power to be minus J 57K, and we have a value for that, or an expression for that. That's minus J omega C V sub C squared. The minus J's cancel, and we can solve for C by dividing both sides by omega V sub C squared. We now have 57K divided by 377, 500 squared. Go see Josie for that 605 microfarad capacitor. And that will now reduce that angle of that 3 combination, a capacitor, load 1 and load 2. What's the angle now? 0. Let's now look at what that does to us and see if we can then understand the benefit of why we did this power factor correction. Let's look at the load power incorporating this capacitor. And so I'm saying after power factor correction. Now we have, let's say, S load is S12 plus S cap. We had 72 plus J57 plus a minus J57 kVA, so that now our S load is 72 kVA. And you might say, so what? Well, now you want to compare what's this giving us, or what's the benefit of all of this. And one way that we could compare that is by examining what's the current now that the source needs to be supplying in order to make all of this work, in order to have all 3 of those loads satisfied. What is the new current magnitude supplied by the source. And what's the first equation that you might think to be using? Is that okay? Or this could be, this is the same. Let's just say that that's the source current. It's all in the same circuit, but we can now take the absolute value of both sides, and we can now say that the magnitude of our source current is the magnitude of our load, the apparent power of our load, divided by the magnitude of our supply voltage, which is what we were calling, I think, V sub G before. We just wrote down that the complex power, the apparent power of our load is 72 K. We're still supplying that with 500 volts, and this now becomes 144 amps. Do you remember what the current was, magnitude, without the capacitor? Do you see the savings? And if we had any kind of, let's say, resistance in the transmission line between the source and the loads, that's going to be I squared R losses. We square 144, that's not going to be nearly as big as squaring 184. So by reducing that angle, we have now reduced the amount of current, or the magnitude of the current, that the source needs to be supplying or delivering to the loads. And if it wasn't clear, the source magnitude was 144. That was the new source current. And that is quite a bit less. Well, here's another. So this source, I sub G, or I source, equal 144 is less than I sub G equaling 184. But we can even look back at what we were doing when we went a little bit aside. And what was load 1's current? 160, what? 160. What in the world? The source is giving us 144. I'll see you next week. So this is now 160 amps, which was the magnitude of I sub 1. This was the current magnitude for load number 1. What is happening? What's actually happening is this sharing or exchanging of magnetizing VARs between the capacitor, or capacitors, because load 2 was capacitive, and we introduced a capacitor, and the inductive behavior of load 1. They're playing locally, and the source doesn't have to worry about what they're trading back and forth at the load side of that transmission line. And they're able to supply each other with what they need overall, so that capacitor is working in concert with that inductive load, and it can now deliver to that inductive load 160 amps, even though the power company is only giving you 144. Let me see if I can write that down. The loads, load 1 and 2, the loads and the capacitor, here I'm saying the capacitor is that capacitor that we introduced for power factor correction. The loads and the capacitor are exchanging stored energy via reactive currents. And these reactive currents circulate between the loads and the capacitor, and as a result, and do not have to flow across the lines from the source to the loads. That reactive current can now be exchanging energy, stored energy, at the load side and not have to worry about what's needing to be transmitted from the power company or from the source. And that's a good thing. Now we have been able to reduce what we're seeing flowing across the transmission line from 184 magnitude amps down to 144, if I'm getting those numbers right. And that's a significant change by introducing that capacitor. And if we didn't get that angle all the way down to 0, maybe the current's not quite at 144, but it's less than what it originally was. Questions on that? Yes. So on the circuit diagram, I don't even have a circuit diagram, do I? Here's my circuit. So I don't even have, and it's not easy to do unless you start maybe looking at the time domain characteristics of these powers at both or all three of those different subsystems, load 1, load 2, and the capacitor. All we can sort of say is that that capacitor is now accommodating the magnetizing bars that load 1 and 2 are requesting. And they're requesting 57K kilobars. And the capacitor is able to deliver that because really they're just complementary. One builds up and the other one is giving back. Then the other one, the magnetic field collapses and that just goes into the capacitor's electric field. The electric field, so you can just sort of think you're playing the accordion. Right? But that's the idea. You're just trading back and forth. One builds and the other one collapses. You collapse and you accommodate what they need. that's as good as I'm going to do with this circuit diagram, is pretend that I don't know, playing some instrument. Yes. So why make these facilities seem inductive rather than capacitive? It's because of the way we build motors, essentially, or machines. They have a lot of, if you've ever torn apart a motor, there's just coils and coils of wire. And that looks essentially like a lot of inductors or an inductance. And it's just the natural way that we physically build these machines. They now look like they are inductors, and we don't have, well, we have capacitive banks, but they are not usually the things that are driving or being used to mechanically move things through a plant or do some particular task in an industrial setting. So it's just the nature of the way that these physical pieces are built or constructed. They look like interconnected R's and L's. And that's what most of them look like. So now if you introduce this capacitor bank, you're able to sort of offset or reduce some of that inductive look to what that overall plant is. Was there another question?
So trying to set Q equals 0 is going to give you the most current without it.
Yes, so setting the comment or statement, I don't know that it was a question, but the statement was selecting the Q to make the angle 0 will give you the best angle, or theta equal to 0, without actually going in the wrong or more in the negative direction of your Q. So you're now trying to hit this, and in reality, these are probably fluctuating, and you would probably want to select a capacitor, or you have a bank of capacitors that you can switch in and out to adjust that Q from your capacitor bank to accommodate the needs of your machines that you may be turning on and off. It may not look always like a static inductor of a certain size. Is that other questions on this? That's chapter 10. Let's now go into chapter 11, which is three-phase power. And to begin, let me just write some things down, which I'm labeling as characteristics of three-phase power. One is with three-phase power, we can move large blocks of power, or large quantities. And typically we do that with high voltages. Why do we want high voltages versus high currents? We know from the beginning of your electrical engineering circuits that power is VI, right? Now we've generalized that to be a complex power of V phasor I star, or I phasor conjugate. Now, if it's this combination or product of V and I, why don't we use big I instead of big V? Give me a V. Give me an I. I don't know how to do. What are we going? Why are we picking big V's instead of big I's? Big I. Transformer? So we can use transformers, can't we, to raise and lower voltages pretty easily. And if I'm sitting here at Tucson and I want to deliver power out to some distant location, there's a wire between me and that distant location. And that wire inherently has some resistance, doesn't it? And what's the loss? If I lump that resistance into just an R, I now could say, oh, that power lost between here and there is I squared R. And if I can reduce I, then that loss won't be as big. So I know I want this much power, and that power is the product of V and I. You guys are going to remember this, I hope. So now you have V and I. If you have a big V, you don't have as big of an I. And that I squared R loss won't be as large. That's why you're wanting to transmit these large blocks of power with high voltages. And the nice thing is that we can obtain high voltages using these things that have a bunch of coils of wire, which are transformers. So can obtain high voltages using transformers. And when do those transformers work? What kind of voltage do we need? And now I'm assuming we have two types of voltage. And what type of voltage were you using mostly in 220, in the early parts of 220? DC. You need AC, varying time domain voltages for these transformers to even work, and which is one reason why we have sinusoidal voltages. So these transformers, when the voltage is AC, when it's DC, then we have to do something else to try to maybe make these voltages higher than what they want to be when we generate them or when we want to use them. Can obtain high voltages using transformers when voltage is AC versus maybe you're using rotating machines to convert a DC voltage from a low value to a high value. And those DC machines are moving mechanical parts. That transformer just sits there. Obviously, you have to wrap the wire up, but it's just a static device versus using rotating machines to raise and lower voltage when you have DC voltages. Or another way of thinking of that is now this AC, a transformer is less complex than this rotating machine. AC implies less complex system. For raising and lowering voltage. That's one of the characteristics. A second characteristic, and maybe this is the key, it's economic. If you now have three phases instead of a single phase that you might have to go many different or supply many different loads, now we can use smaller and lighter components than single phase or one phase networks. Or if you thought about it, with a three-phase system, you can essentially be driving three different loads. And if you needed to drive those three loads with pairs of wires, we'll learn that a three-phase system can have an A-phase wire, a B-phase wire, and a C-phase wire, and maybe a ground wire. So we have four wires. If we now had three loads that each had two wires, how many wires do we have there? 2, 4, 6. So now we're trading off 4 wires in a three-phase system versus 6 wires in this same, let's say, network of 3 loads that we're trying to derive as single-phase systems. So there's an economic payoff to doing three-phase. Also, the performance is better. In a three-phase system, we won't necessarily show it, but we actually have a steady torque supplied to the machines. If you remember looking at some of those sinusoidal power curves, they were just going up and down, up and down, up and down at twice the frequency of our voltage and current. And now if you thought about driving some shaft with that time varying single phase, it's going up and down, and the torque is not steady. But with three-phase, with a three-phase motor, you can actually have a nice steady torque applied to that shaft because you have the A, B, C, A, B, C, A, B. They're going to think we have preschoolers in here, especially when we're not going above C. A, B, C, A, B, or they'll think the instructor has gone off the deep end, right? I don't even have to say ABC for that to happen. So this, if the torque is steady, we have less vibrations. And a more efficient system. Another characteristic. Another is we are going to be playing with balanced, and this will make more sense as we go, but everything is basically, each of these phases looks the same. That's what we mean by balanced. So with balanced three-phase power, we actually are looking at, again, economic reasons. Because actually there will be no current flowing in the neutral conductor when everything is balanced. And if there's no current flowing in that wire, there's no I squared R loss, so there's no power lost. In the neutral conductor. And with learning balanced three-phase power, that's the best place to start in terms of learning these concepts, because some unbalanced circuits or some unbalanced conditions can be solved by what are referred to as symmetrical components. And those symmetrical component ideas are relying on our understanding what's happening with balanced systems or with balanced operation. Those are some justifications for spending the next period of time learning about three-phase power. That's now motivating, hopefully, why we want to do this. Let's look at a system or a block diagram. Again, this isn't really a circuit diagram, it's more of a block diagram, but here we have a block diagram of a three-phase system. What do we have? We actually have our source, and that's, in this class, it'll traditionally be on the left. Then we have three wires coming out, at least three wires. Maybe we have a neutral if we have a Y connection. We have three wires that now need to go through this transmission system. Maybe we want a transformer to raise up those voltages to get them really high. So now we might have transformers and transmission lines. And then we go over to our three-phase load or loads. We, in this class, are not going to worry about transformers. That's log. Have you seen that before? Log. Transformers are log. Without loss of generality. So without loss of generality, we're going to not worry about the transformers. We'll just be always saying we're going to be at high voltage, and we'll worry about the high voltage aspect of what's going on. So this WLOG is without loss of generality. Or the transformers can be omitted in our discussion. Really what we will have is we will have a source, a three-phase source or three-phase sources. We will have transmission lines, which might be represented by resistors and inductors. And then we will have loads that we will try to service or accommodate. What do three-phase voltages look like, or what can you start to be thinking about? Relative to what you've already learned. How can we relate that to what we've already learned? Now I've said that we have three different phases. We are going to have an A phase. Let me call that V sub A. And let me just label that A phase voltage at the reference, let that be my reference, and I'll give that a 0 angle. That's now at 0 degrees. And now I'm splitting my pi. These are balanced three-phase voltages. All of these lines are supposed to be the same length, whether I draw them accurately or not. But now I have the B phase, and that should be 120 degrees behind the A phase. And then the C phase, and again, those should be the same length. That's 120 degrees behind the B phase. All of these phases in a balanced system are 120 degrees apart. Where now V sub A as a phasor might have some magnitude at an angle of 0 degrees. And that's the A phase voltage. If the B phase has the same magnitude as the A phase, I think you can already write most of this expression down. It's just V sub M, and what's its angle? We typically keep these angles between 180 and 0. So this will be now minus 120 since it's behind V sub A. And this is now the B phase. And the C phase has the same magnitude. It's now minus 240, but we've agreed maybe to keep everything between plus and minus 180. So that's actually equivalent to being at plus 120 relative to the A phase. And this is now our C phase. And this is actually a positive phase sequence, balanced three-phase set of voltages. And the way that you might want to think about that is suppose you're sitting right here. We're getting back to that eye again. Here's an eye. And it's watching these phasors move past it. And these phasors move past, or they're rotating. How fast are they spinning? 60 hertz. So these guys are spinning, but we usually just take a strobe-like picture, and A is now at 0. And when A is at 0, B is at minus 120, and C is at plus 120. That's the picture we're drawing. They're rotating, though, in a counterclockwise rotation. And which phase do you see first if you're standing right there watching? And hopefully it's not a blade, because you'd have to be pretty fast to be jumping at 60 hertz. Well, the whole thing is spinning 60, so that's now 30, or 3 times faster than that, right? Let's play jump rope. It's much faster than you would be jumping rope, right? But which phase do you see first? A, then which one? B, C. A, B, C. This is the positive phase sequence, and I hope you can anticipate what the negative phase sequence is going to look like. This is now the positive phase sequence. Or the ABC phase sequence, and I hope you can see where the ABC comes from. What's the negative phase sequence going to look like if that's the positive phase sequence? And again, let's have the A phase being our reference phasor. The negative phase sequence, or the ACB sequence, if this is now V sub A, I'll do the hard part. There are my other phasors. Oh, I forgot to label them. Which is which? If these are still spinning counterclockwise, and this is supposed to, if I'm still sitting here looking or observing, I see A, then I see C, then I see B. So this is now V sub C, this is V sub B. And from that, I think you can say that now V sub A is V sub M at 0. V sub B is what? It's now plus 120, and V sub C is minus 120. And what you need to keep in mind is if you have a positive phase sequence, you can connect these different loads or sources in parallel, but you can't mix phases. You can't have a positive sequence with a negative sequence in parallel. Everything has to be one phase sequence. We'll pick up at that point on Tuesday. Don't forget your homework is due Sunday evening.